Greetings, friends of astrobiology. Welcome to a brand new episode of Ask an Astrobiologist, a show where we celebrate science and celebrate scientists. My name is Sanjoy, and this program is made possible by contributions from the NASA Astrobiology program and the non-profit Blue Marble Space. Last month, my fiercely bearded and wonderful co-host, Dr. Graham Lau, interviewed Dr. Jason Wright, and they were speaking about exoplanets. And this month, we're going to come slamming back to the Earth, literally, with our wonderful guest, Dr. Gordon Osinski, a professor at Western University in Canada and an expert in impact cratering processes. But first, it's time for your favorite background quiz. Mike, if you could put up the background from last month. It was this beautiful geyser. Many of you got it right. It is, of course, the Strokkur geyser in Iceland, located in the Haukardalur Valley. Also, of course, in Iceland. It's the most active geyser in the world, erupting roughly every 5 minutes. But nearby, not even 50 meters away, lies a much bigger pool of Geysir, the geyser that gives its name to all the other geysers in the world. Geysir erupts much less frequently, on the order of years, and it's a much bigger, much more intimidating pool. Locals have known to have made it erupt by by downing the water level in it, which triggers an eruption, and some have also thrown soap in it that have also triggered an eruption. Of course, that's frowned upon today for environmental concerns. It's not the largest geyser, however. The largest geyser is in the Waimea Valley of New Zealand, but it's now extinct. Last erupted, I think, in the 1910s. So we have 3 winners, and the winners are, our first prize goes to @GeoTwits. Congratulations, you got it right with the Haukardalur Valley. The second place goes to @MailSC, and the third place is @GeoTwits, second place @MailSC, and the first place is Mike Belan, tweeting as @ForMike's sake. So congratulations to all of 3 of you. You'll get to the prizes, which is a combination of the Astrobiology comic books, the mugs, and some other prizes that I don't have on top of my head, because today is spring cleaning and I don't have the items with me. But it's all good. I also want to give a shout out to all of you who are doing a lot of efforts tweeting about our show, and on Facebook, on Twitter, on SaganNet, and elsewhere. Please keep doing that. We're very grateful to try and increase our participant levels every episode. So thank you so much for those of you who spread the word. And in order to reward that, we started an Ambassador of the Month for Ask an Astrobiologist. So the one of you that we see is the most active at helping us spread the word about Ask an Astrobiologist will be called our Ambassador for the month. So the Ambassador for April 2019 is Marianne Denton, who is amazing, who has been an amazing supporter of the show. So congratulations, Marianne. You'll be receiving the background, the actual background of the show will be sent to your home. So congratulations. Again, help us share the word about Ask an Astrobiologist. It's a show we're really excited about, and I hope you are too. If you have any questions during the program for Dr. Osinski, please use #AskAstrobio on Twitter, or ask them directly on Facebook Live in the comments down below, and on SaganNet, of course, the home of Ask an Astrobiologist. So without any ado, it is my great pleasure to introduce Dr. Gordon Osinski, a professor at the Western University in Canada. Dr. Osinski, thank you so much for being with us today.
Oh, it's a pleasure and an honor, Sanjoy.
The concept of impact cratering is something we think about as happening on other planets, the Moon and Mars, but it also has happened quite a bit on Earth. Perhaps we can start this conversation by you telling us about what is an impact cratering process and why it is important to study.
For sure, yeah. It's one of those processes that even undergrad geologists often don't get, during teaching, and so it's a bit of a off topic. It's not mainstream. Often people know about volcanoes and plate tectonics perhaps on Earth. But really over the last couple of decades in particular, we've become aware that, as you say, you can look up on the Moon on a clear night and see all these pockmarked surfaces. Various rovers have been tootling along the surface of Mars for a number of decades too, often going from crater to crater. And so we know other planetary objects have been hit by asteroids and comets since they were formed, 4.5 billion years ago. On Earth, around the turn of the century, a meteor or Barringer crater in Arizona was kind of first proposed to be an impact crater. But it wasn't until the 1960s and 70s where, people really started realizing that, that things do hit the Earth. It perhaps sounds a bit ridiculous now that, the Earth would, everything would bypass the Earth. And in fact, because Earth is bigger than the moon, more because of larger gravitational cross-section, we should look worse off than the moon, which, speaks to how active our planet is.
Fascinating. So how did you become interested in impact processes? You mentioned that it's not typically taught in the classical geological curriculum. And perhaps you can share your experience when you first went to a crater yourself, probably as a student. Like, how was it like? How did you feel? Was it a humbling experience?
Yeah, for sure. So, yeah, I mean, I did a very traditional undergraduate degree in geology at the University of St Andrews in Scotland. And, I vaguely recall hearing the word Sudbury related to economic deposits there. But even that was debated, that Sudbury was an impact in class. I do remember that. But that was about it. We had a little bit of a planetary component in that degree. And so it was honestly approaching the end of my undergrad, I think, like many students, wondering what I was going to do with my life, and I thought I'd like to travel overseas for, initially just a master's, and literally just stumbled across this project advertised. It was three big things caught my eye. It was working on impact craters, which sounded fascinating, not something I knew anything about, so I always liked a challenge. It was working up in the Arctic, which brings me on to the first crater I visited, and it was also working, with NASA and with space kind of organizations. And so literally finished my undergrad, had my viva. A week later, I was on a plane to Canada, to New Brunswick, where I did my PhD. And then about 2 weeks later, after that, I kind of did some crash reading in impact craters. And then, my first crater that I ever stepped foot on is probably one of the most, beautiful and fresh and well-preserved in the world. And that's the Horton crater on Devon Island in the Canadian Arctic. So, from that standpoint, absolutely spoiled. That was my first introduction to impact craters and what they looked like. And Devon Island is not just an impact crater, but it's a barren polar desert environment too. So it's just a beautiful, beautiful part of the world and some spectacular geology.
So how long did you spend up there? What do you do? And what differentiates a crater from a larger, big depression in the ground? Like, how do you tell that it was in fact an impact?
For sure. So, during my PhD, a lot of it was, and what attracted me to geology in the first place is actually, the field work, the field aspects of things, being outside. And so, for the first 3 years of my PhD, I spent a couple of months up there. And, that's pushing it up in the high Arctic. I'm still going back there, but basically it's snowing in June, and the snow starts again in August, and even in July it snows. So, you got a very short window for field seasons. So a lot of geological mapping. I actually created a geological map of the Horton crater, which meant I could apply my traditional geological tools to this kind of new topic. And then, a lot of sample work back in the lab. Yeah.
So NASA is also very interested in impact cratering processes for reasons that are obvious in the sense that they exist in higher density on the Moon and Mars, and in fact they've been useful for analog studies in terms of training astronauts in geological processes, and that has been done at Horton crater. And I think you've been involved in some of these simulation missions. Could you tell us a little bit about these?
Yeah, for sure. So, yeah, I mean, during my PhD, it was the peak of this Horton Mars project that was led by kind of SETI and the Mars Institute and NASA Ames. And I got to meet amazing people. I met astronauts during my PhD, a bunch of NASA Ames folks. Terry Fong and his group brought kind of robots up there to test and develop. I got to wear a prototype spacesuit from a company, which was, as a green PhD student from the UK who actually really didn't have much of a, I came into my PhD not being, a super big space advocate, and it didn't really grow up, wanting to be an astronaut, perhaps like other people. And so I was just immersed in that. And, I learned a lot during my PhD about, planetary science in general, which again, I didn't really have before I came to Canada. Yeah, and these analog sites, I've continued that since, not just on Devon Island too. And actually, just yesterday, the Canadian Space Agency announced an award we've got, which is actually focusing on the Moon. So this is not for astrobiological reasons, but impact craters from a geological standpoint, really percolate the all over the moon. And, it's an important process to understand there and, for retrieving samples from too.
Cool, very, very cool. I've never done such a simulation. Sounds like a lot of fun.
Yeah.
So there are two main causes of impact craters, right? It could be an asteroid strike or a comet strike. Is there a way to tell the difference from the field, or is it something that you need to do more advanced calculations to determine?
Yeah, for sure. No, there's no way of knowing when you're out there, and you actually asked an earlier question too that I didn't answer, which is how do you even know you're in a meteorite impact crater? And so there's only one diagnostic feature. It just so happens that Horton has a lot of these, and these are shatter cones. If you have very good eyes on the shelf behind me, I know I have a bunch lying up there. But these are essentially kind of striated surfaces that the intense pressures and temperatures of the impact event cause in the rock. And then really everything else, and then back to your kind of comet versus asteroid question, really involves a lot of laboratory-based research, a lot of microscopy, electron microprobe, scanning electron microprobe work. To differentiate between comets and asteroids, you get into various different isotopic systems. Looking for things like iridium is maybe the one most people might be familiar with. You're looking for elements that are not very abundant or absent on the surface of the Earth, but could have been brought here by the projectile. But even then, it's incredibly difficult. For example, at Horton, some of the best folks in the world at this have looked and have not been able to determine any projectile signature. So, we don't have any idea of even what kind of asteroid, let alone whether it was a comet. So it's a really difficult thing to do.
So there's not even traces of like those high pressure minerals or like reversed stratification on the crater rim. Do that?
Sure. So you see those kinds of things and other effects in the rock, but those are generated, in the rocks that were there in the target, not brought there by the asteroid. And, this is maybe a bit of a sidetrack into, how impact craters form. What keeps me interested is that it's unlike any other geological process. The most violent volcanic explosion craters, and I think you've got one behind you there, these pale in comparison to what happens during an impact event. We generate temperatures of tens of thousands of Kelvin and hundreds of gigapascals pressure. And, what that typically does is vaporize most of what came in. So most of the asteroid and comet is just simply obliterated, which is why it's hard to find a trace in these larger impact events. But yeah, absolutely, the crater form, these high pressure polymorphs and other features we do see at Horton and lots of other craters.
Very cool. Yeah, so the background behind me, those of you who are watching, make sure you try and figure out what it is for next month episode, and then we'll announce the winners then. Gordon, you've been talking about iridium layers in a conversation just a few minutes ago, and makes me think about the Chicxulub impact crater, perhaps the most famous impact on Earth today, the one that theoretically wiped out the dinosaurs about 65 million years ago. Are you doing some work there? Can you tell us a little bit more about that impact and how are we narrowing down to that being the cause for the extinction of the dinosaurs?
For sure. It's a little bit of a controversial topic, I think, still. But, again, like you say, Chicxulub is one of, I think, probably the most famous impact crater in the world. As a community and a scientific community, whatever you believe, with respect to the mass extinction event, we have a lot to owe to Chicxulub because it's one of those, major points. I think, two big things in the last few decades that really spurred interest in meteorite impacts, and the fact that it happens today and has had major, not just geological effects, but environmental and biological effects, was the impact of comet Shoemaker-Levy 9 in Jupiter in the early 90s. And then, beginning with Walter Alvarez's paper in 1980 that suggested there was an impact at that time. But it then took, to the 90s to discover Chicxulub and then to link it to that boundary. And so it generated an inordinate amount of interest and, I think really brought to not just the scientifics, mindset, but, to the public that, big things happened, we think. And I think, the pendulum swings back and forth a little bit. But I think the overwhelming evidence is that, that was the major factor, perhaps not the only one. But that impact, 66 million years ago in what is now Yucatan Peninsula in Mexico, did create, 2/3 of species on Earth, including the well-known dinosaurs, to go extinct.
There was a paper that was published, I think, about a month ago, which about a new query in the Morrison Formation in the United States, where they found apparently dinosaur bones and fish all together in the same layer with like impact debris, which is absolutely mind blowing. Kind of a snapshot of the catastrophe. Now
Yeah,
it's
yeah,
still
for sure.
controversial whether that's true, but
Yeah, no,
it's
that was an amazing paper, and yeah, I think they recorded, there was these spherules thrown out
that's
by
right.
the Chicxulub impact in fish, inside fish, so they were literally choking on the ejector thrown out by the Chicxulub impact. What is, well, even then would be, hundreds of thousands of kilometers away, and yeah, I mean, I think this is the major aspect of impacts, and people are maybe wondering where we're talking about impacts in an astrobiology setting and an astrobiologist, because a lot of people think of these destructive effects. But what I've been interested in more, and actually what I'm studying at Chicxulub, is the potential astrobiological significance of impacts. So after they form, they actually, I think, provide benefits for microbial life. And so I've got a student actually working on studying how the Chicxulub impact created a hydrothermal system in that large crater.
Yeah, so that's going to be my next question. In a sense, we think about impact processes as being devastating to planetary surface and to the life on it, but ironically enough, it can create environments, local and even planetary wide, that can sustain at least a habitable environment for longer duration, as has been hypothesized for Mars, and also locally via those hydrothermal systems. So perhaps you can tell us more about how those hydrothermal systems form following an impact, and how that can maintain an environment for life, and perhaps how long do they even last?
Yeah, for sure. I mean, lots of questions you just threw at me, so remind me if I've forgotten to answer them all. But yeah, this is really the last kind of couple of decades that it's the realization that, yeah, and I've used this in proposals, that impacts create beneficial effects, and definitely the primary one, the most obvious, I think, and the most kind of spatially extensive and common, are hydrothermal systems. So, hydrothermal systems form anywhere on Earth today where you have a heat source plus water in close proximity. So if you think of Yellowstone National Park, Iceland, New Zealand, you had the geyser, the image of the month from last Ask an Astrobiologist, was a geyser. So, basically you have volcanically active regions. So you have hot rocks, even magma at depth. If groundwater or rain or seawater interacts with those hot rocks, that water heats up, can dissolve, minerals and rocks in one area, rises to the surface, sometimes as geysers and as hot springs, cools down, and then, recirculates essentially. And I don't think it comes as a surprise today, although it did when people first looked at this, but, impacts deposit a huge amount of energy into the crust of any planet. Most of that energy ends up being essentially, deposited as heat. So you can generate many cubic kilometers of what we call impact melt. So essentially you melt large portions of planetary crusts, and then that, magma essentially sits on the surface of a planet for sometimes hundreds of thousands of years cooling down. So that's one of the major heat drivers. The other, and it becomes a more major component in these bigger craters. If we go back to Chicxulub, we know in these large craters that the rocks in the center are uplifted from depth, and sometimes, as many as 10, 20, even 30 kilometers. And we know as you go down in the Earth's crust and in any planet, the rocks get hotter. And so you kind of instantaneously bring hot rocks that were originally, 20 kilometers down to the surface. And then, depending on the setting, Chicxulub actually impacted into a shallow sea. So, you had a lot of seawater running in. Of course, rains on Earth, but it could be melting ice in other locations. Put those two together and you can generate a hydrothermal system.
And those are really important because the chemical energy in these waters can be utilized by life. So life does not necessarily need to be at the surface and depend on light. You have plenty of life on Earth that exists in the subsurface that survives based on the chemical energy that's released by the dissolution of minerals in rocks, which is awesome. So
Yeah,
it really makes
absolutely.
you think about where else in the solar system or in the galaxy, in the universe, you could potentially find life.
Yeah, for sure. And I mean, again, it's debated like almost everything in science, but we still think one of the places life on Earth may have originated is in hydrothermal systems. Typically in documentaries, it's the black smoker type of idea at the mid-ocean ridges, so associated with volcanic heat sources. But yeah, what this really does is open the door, as you kind of hinted at, to many planets, or most of the objects in the solar system may have been active volcanically early on, but they're not today. So their surfaces are relatively cold. But even on present-day Mars, one could speculate that you have an asteroid slamming into the northern plains where there's lots of ice in the subsurface, and it would likely be shorter-lived. But that could melt any H2O that's around and generate a transient hydrothermal system. Asteroids, small other objects that we may not have thought about having the habitats for life. The very fact that asteroids and comets don't really care what they hit. They pervade the solar system and other solar systems outside our own solar system. Again, it kind of opens the door to rethinking planetary habitability.
And so thinking about Mars in that same vein, there's always this controversy between the warm early Mars and the cold dry Mars, because we see these evidence of flowing riverbeds, of course not flowing today, but they're dry riverbeds on Mars, suggesting that water was flowing for a fair amount of time in the early days, which contrasts to the very thin atmosphere we see today. And so one theory, among many others, is that they had large enough impacts in the early days of the solar system that are large enough to create a temporary planetary atmosphere that can sustain liquid water for tens of thousands, maybe hundreds of thousands of years, which is a long time as a human, an instant, geologically. But again, like you can change the surface environment of a planet based on high energy impacts, right?
Absolutely, yeah. And I mean, we could take that even one step further. And, this is clays on Mars. Another big reason we think, or people have suggested Mars was warmer and wetter in the past is because we see lots of minerals that have, that are what we call hydrated. They have water and other sulfates is another good example where, they require water to be around for their formation. We see clays all over the heavily cratered highlands. And, most people think that those are just being excavated from depth by impacts. But my research scientist, Livia Tornabene here, and I have published on this, and, we've thrown out the idea that, not all, don't get us wrong, but, maybe many of those clay occurrences we're seeing on the surface of Mars are actually generated in impact-generated hydrothermal systems, so very localized, and they actually don't care about the surface climate. This could be happening on a cold early Mars, generating clays in these impact-generated hydrothermal systems. And so, I think the more we learn, the more we study impacts, I think they're becoming, I hope anyway, increasingly understood as a driver of planetary evolution and, evolution of the biosphere too.
Very cool. Yeah, because clays are extremely fine pieces of rock all mushed together, so the common thought is that rocks have been transported over a long time and breaking down over the transport process to eventually be sedimented out of a water environment into very fine clays. But if you can form them in a completely different mind setting, that changes the game about what the clays mean in terms of environmental markers.
Yeah, no, absolutely. Yeah.
Very cool. Very cool. So if you have students that are interested, and among our viewers, I'm sure, who are interested in learning more about impact cratering processes, or even want to go to school to become experts in impact processes, what advice would you have for them?
I mean, the neat thing I think about it, about impact, studying in meteorite impacts, planetary science in general, is that you can come at it from quite a few different angles. Today there's still a big role for people with a geoscience background in studying meteorite impacts. The whole crossover, though, now into astrobiology, there's a need for people, I think actually more people with, a geobiology, microbiology background are working on impacts. A lot of people, though, are modeling impact craters. There's a lot of physicists and computer science students out there with those background. And we do, we kind of need everything. It's one of the challenges that, I tell students and the public about impacts is, it's a challenge, but it's something we're glad hasn't happened, is that, unlike volcanism, what would be the first thing you want to do as a volcanologist studying old ancient volcanic rocks? Well, you go and witness a volcanic eruption happening. So you look at the process to try and figure out the product, especially the ancient product. And, we haven't had a large meteorite impact on Earth in human timescale. Which is good, for our species, but it means we're left, trying to figure out, connect the dots. And so, there's experimentalists, there's room for modelers, There's room for the geologists and the biologists. And so, yeah, you can come at this from a lot of different angles and a lot of different perspectives.
So you can be like a geologist in the traditional sense of looking at rocks and identifying the minerals, or you can come at it from the physics and doing computer simulations of impact cratering processes. So it's really a broad approach, and we need a bunch of different scientists to really understand them. That's very cool. And then you have events like that Chelyabinsk, about a couple of years ago in Russia that remind us that we live in an active solar system.
Yeah, we do. And I mean, it's one of those things where, impacts don't hit the Earth very often, but, meteor craters only 50,000 years old. We've got records of other crater-forming impacts in, on the thousands of years time scale. And so, yeah, it might be 100, might be 1,000 years from now, but we'll have, likely some small event to study sometime somewhere. Hopefully it's in a remote location, but yeah.
We're thankful that there's a lot of ocean on the Earth to host these impacts. If you have any questions, again, those of you who are watching, please use hashtag #AskAstrobio on Twitter, or ask them on Facebook Live in the questions down below, or on SegaNet directly. So perhaps my last question before we open it up to questions. I mean, I love this conversation. I could go on forever, but I'm already seeing the teleprompter explode from our audience wanting to ask you questions. Perhaps you can tell us some of the places on Earth where you've traveled to explore different craters. If you have any fun adventures or stories that occurred in them.
Yeah, I mean, again, I kind of hinted at it earlier. One of the things that got me into geology in the first place after school, because I think, again, like most, geology is not something taught too much in schools, was that, the love of the outdoors. In my spare time, the little time I have, I'm typically out climbing or mountain biking or skiing. And so, it was actually that, being outdoors that attracted me to geology. And, still today, my kind of happy place is in the field somewhere. So I'm getting ready for another trip up to the Canadian Arctic. This will be about the 20th year working up there. So not going back to Horton this year, but for kind of other non-crater related field work. But I've been kind of slowly chipping away at the Canadian impact record. Canada, probably next to Australia, has the biggest concentration of impact craters in the world because it has a lot of the old ancient Canadian shield rocks. And so I've had the pleasure to do work in northern Labrador, northern Quebec, northern Saskatchewan, looking at these, incredibly remote craters. I've been flown in by helicopter, float plane, twin otter and tundra tires up in the Arctic. And, you literally get dropped off in the middle of nowhere, and then it's, well, see you in 2 weeks or a month kind of thing, and you hope they come back and get you. So, yeah, lots of stories. I submitted my first sabbatical about 3 years ago and did some field work at some of the Australian impact craters, actually. And that was great, too. And again, similar, but actually even more isolated. A teeny little two-seater, three-seater helicopter, and I actually had my son along with me then, and dropped us out in the middle of the outback. And we'll see you, and we'll see you in a few days.
Very cool, very cool. Yeah, I mean, being a geologist myself and having done quite a bit of field work, it definitely adds to the motivation of being trapped in an office for most of the year, writing proposals to get those field trip funding.
Yeah, it's the light at the end of the tunnel.
Yeah. So now it's time for the questions, which is awesome. I'm very excited. Thank you all for your questions that you've been sending them. So the first one, Gordon, is from Amanda Lau, who is asking from Facebook, do you think that the idea of panspermia still makes sense? Can life survive an impact?
Oh, that's a great question, and there's almost actually two there in one. So the last bit, can life survive impact? The answer is yes. Even for example, at the Horton crater in the Arctic, I did some work in collaborations with a chemist, John Parnell at the University of Aberdeen, and he showed that a lot of the organic molecules in the rocks, even the ones that were heated and shocked to high pressures, survived. And what I think is most I haven't done this myself, but people have done experiments at actually NASA Ames and at NASA Johnson. They have these high-powered experimental guns that are literally, creating on a small scale impact events. And I know what they did. They impregnated, rocks with bacteria, shot a projectile at them at a super high velocity, and a certain portion of that those organisms survive. And so panspermia, that end is possible. People have put most of the pieces together now, I think. people have done experiments on re-entry. A good friend of mine who actually got me, I think, probably into astrobiology, Charles Coquelle, who's now at the University of Edinburgh. I don't know how he got permission, but he convinced the Russians to strap rocks to the outside of a Soyuz capsule, and that re-entered the Earth's atmosphere. And some of the organisms in those rocks survived, that high temperature re-entry. And then we know, they've done experiments on the space station that things could survive high radiation environments. So, yeah, I'm not going to say I agree and I'm a panspermian, but I think it's potentially bits of that hypothesis seem viable for sure.
If you all are watching, are interested in this idea of strapping rocks to the side of the space station, Charles Kell was actually our very first guest for Ask an Astrobiologist a long time ago now, 22 episodes ago. Yeah. And if you can find this episode on YouTube, so to refresh your memory. So very cool. Thank you. The next question comes from Anthony Vinci Guerra on Facebook, and he's asking about the Drake equation and what do you think of it, and is it still relevant for life?
This is definitely kind of outside my area of expertise, but I think it is still relevant. But in our own solar system, we're learning of it as a gross estimate of of potential for life out there. I do think it works, but I think actually impacts create a bit of an issue for that equation, and it doesn't account for the fact that on small bodies in different parts, out of the Goldilocks zone, out of where water is stable, you could create habitats for life on in various different parts of the solar system without the need for long-term stability of water too. So yeah, as a fundamental base level, I think it's still a great thing, but there's definitely, I think, probably more and more exceptions.
Indeed. So that leads actually to the next question by Michael Cooney, who on Twitter asks, do you think habitable environments actually do exist elsewhere in the universe? Are there stronger locations such as Mars or Europa where you would expect to find signs of life?
Yes. I think I still think Mars is, as a great place to go to. And again, we have discovered, based on remote sensing data, for example, we think some of the impacts on Mars created hydrothermal systems. So I do think the habitats were there. We know the ingredients were there, and then it's just a question, did life originate there? Definitely, some of the outer moons of our own solar system are high priority astrobiological targets because we know that, liquid water exists even today. And again, impacts could be part of that story in delivering nutrients and also, creating hydrothermal systems and other habitats that create them and make them even habitable today. And then again, as I hinted at earlier, our knowledge, basically, unless we fundamentally misunderstood how solar systems form, impact events, so an object hitting another object is going to be pervasive throughout the entire universe in every solar system. And so, impacts is something that's ubiquitous enough that, you tie that with other things and the number of stars out there. I think that there must be some habitable environments, and maybe one or two created by impacts.
Yeah, and seeing, as we've discussed today, as how resilient life can be, it seems crazy to think that life is limited to our own planet. Yeah. So Amanda Lau asks again on Facebook, we talk a lot about Chicxulub like we did today, but were there larger impacts that wiped out life earlier on Earth?
Oh, that's a great question. And so there currently today, we know of about 190 or so impact craters on Earth. If you're actually interested in knowing where they are, I'll do a shout out to a new kind of educational initiative we've got going, which is just impactearth.com. And you can kind of zoom around to your heart's content and see where all the craters are. But we have Chicxulub, Vredefort in South Africa, and Sudbury here in Ontario, that are all around the 200-ish kilometer mark. When we look at the moon, though, and Mars and other planets, there are what we call basins, impact basins, that are thousands of kilometers across. Those size of impacts must have occurred on Earth, but it's just the fact that Earth is so geologically active that we have hardly any record of it, in particular the first billion years of Earth's history, and, virtually nothing from the first 500 million years of Earth's history when those larger impacts happened. Whether there were, other impact-related mass extinction events, I think in the past, when we're talking single-celled organisms, it's a lot more resilient form of life, and so, in very localized, those impacts would have been destructive. But right now, Chicxulub is the only kind of event associated with a mass extinction event in the last 500 million years, so 500 million years.
Very cool. Yeah, I did some field work, I think, 2 years ago on Lake Superior in Canada, and there was some evidence of life trapped in rocks, so in cherts, essentially stromatolites, which are, we talked about in this show before, kind of mounds of biological mats that then have been sliced kind of flat by glacial processes. And up there in Lake Superior, the age is roughly the same as the Sudbury impact. So it was cool to kind of sit down, in this very beautiful, quiet environment on these cherts, which have evidence of life on Earth. And that at the same time period that, just a few hundred miles that way, like, Sudbury arrives and just wipes everything. Like, you can see that devastation in the rocks even today, which is
no, for sure.
very humbling. Balder Veka on Facebook asks, is it expensive to study astrobiology compared to other careers?
I don't. You can make it expensive, but no, I wouldn't say it's so at all. It's expensive for me to go up to the Arctic to do field work at the Horton crater, but it's just a 5-hour drive for me to go to Sudbury. So, and then in terms of the laboratory techniques and the kind of things we look at in the lab, you can there's a varying scale from doing simple work on an inexpensive microscope to applying the cutting edge techniques. So. Definitely not more expensive than any other field of science, I would say.
Yeah, I agree with that. After all, astrobiology is where you take the direction of your science. You can be an oceanographer doing astrobiology. You can be a geologist doing astrobiology. You can be a microbiologist doing astrobiology. You can be an astronomer doing astrobiology. So you're an expert in these independent fields, then you take your research to answer astrobiological questions. So it's not really a discipline almost. It's kind of I see it as a framework on which different disciplines come together to study those really big questions that astrobiology asks.
Absolutely, yeah. I mean, it's like an interdisciplinary crossroads of many, many disciplines.
Which is what has attracted to me to astrobiology in the first place, and I think you as well.
Yeah, me too. Absolutely.
So Graham Lau asks, and I'm glad you mentioned that, Graham, because I was going to ask that too. So Gordon, you work at the Center for Planetary Science and Exploration at Western. Could you tell us a little bit about CPSX and how does it play a role in the broader exploration of Earth and for Canada?
Yeah, I'd love to. I wasn't expected to be asked a question on that, but it's great to have the opportunity. So this is a cross-disciplinary center, like what we just talked about with astrobiology. So I'm in the Department of Earth Sciences here at Western, and, like other universities, we have departments of X, Y, and Z. And so at Western, there's a culture of bringing together, people from various different backgrounds under these centers and institutes. And so we created this CPSX, the Center for Planetary Science and Exploration, about a decade ago to bring together initially engineers and scientists, but it's really exploded to become, we got health sciences and doctors and lawyers, as we're getting into space policy and laws. And, space is really one of those things that is, infinitely interdisciplinary. You can come at space and there's a need for, understanding of space from various different disciplines. And, what's really driving and really what attracted me to Western is the center. And we have Canada's only graduate program in planetary science. And so we get a lot of students coming here from across Canada, but also the US and, overseas too, to come and work in this really fun interdisciplinary environment.
Fantastic. So CPSX, folks, check it out online. Yeah. Perhaps the most violent impact crater, or rather impact, because there's no crater of it anymore, is the one that formed the Earth and the Moon. So not many people realize that the Earth and the Moon emerged from a gigantic impact, like called the moon-forming impact. Yeah. Perhaps you can tell us about the birth of the Earth and the Moon.
Yeah, we've been talking about impact craters, as you say, but, there's a complete scale from, on spacecraft, they form teeny, like micron size, what we would call micrometeorite impacts from the impact of dust particles on a solar panel on the space station. And the extreme other end would be, the moon forming impact. And, we do think that those kinds of giant impacts have played a role potentially in the formation of, the Martian dichotomy. and other planets in the solar system. So basically the idea is that, when the solar system first formed, we didn't just have, the eight planets as they exist now, but there were other protoplanets out there. The estimates, a few, whether it's 2 or 5, who knows. And essentially, fairly soon after the Earth was formed or was still forming, another object, roughly the size of Mars, that we call Theia, impacted the Earth. And, it was a cataclysmic event, stripped off a large part of the Earth's crust. And then essentially what was left of the impactor and the Earth basically formed the Earth-Moon system that we see today. And it still remains, it stood the test of time, and still remains the best hypothesis for the formation of our own moon, and for various things and various chemical evidences that we see on the moon.
Very cool. Yeah, I think it's just fascinating. Next question is from Omar et al. And perhaps another anonymous user who are asking about, do you think there are Earth-like worlds out there in the galaxy for us to find? And if you had to guess, what are the chances of us finding another Earth sometime soon? What would it be?
Oh, again, this is me talking as a planetary scientist and speculating probably as much as you do now, or you would do. I think we think there are Earth-like worlds out there. Statistically, given the number of stars in our own galaxy, there must be Earth-like planets out there. Whether there's life on them, again, that's a different matter. Whether we'll find and discover those, I think, in the past decade, this whole era of discovering planets outside our own solar system, so, exoplanet research has just exploded. And I'm as fascinated, it's not my research area. I find it absolutely fascinating, how we can be discovering planets around stars, hundreds and thousands of light years away. But, with the next generation space telescopes, hopefully getting launched in the next few years, we're getting closer and closer to be able to detect those Earth-like planets. And so, kind of watch that space, as it were.
Fascinating. So Joshua de Borgia on Facebook also asked a question that I'm going to restate a little bit because it's a little bit outside our conversation topic, but he's interested in organic molecules. And can those be brought to a planetary system by an impactor?
Short answer is yes, absolutely. We do think that, people have thought for a long time, actually, that, some of the organic molecules were delivered to early Earth either by comets that we know and think carbon-rich, or by a class of meteorites we call carbonaceous chondrites. And they can be, several tens of percent formed of carbon. And so, whether it's small meteorites kind of raining down on the early Earth, that's one thing. An interesting area that I'm just starting to really think about myself is, I mentioned earlier that most of the projectile gets vaporized during an impact because of the high temperatures and pressures. There are exceptions, particularly when the velocity of the impactor is low enough. And one could imagine, a big carbonaceous asteroid, carbon-rich asteroid striking early Earth when there was water around, perhaps that very same crater generating a hydrothermal system. And, so not only having the habitat for life, but potentially the ingredients for life, and putting the two and two together. So I know that's pure speculation, but we can do that on the show, I hope, a little bit.
Oh, absolutely. This is what this is about. Our next question is from Anonymous. So we talked about craters on Earth as being good analogs to craters elsewhere. And this person is curious about actually what makes an analog a good analog to an extraterrestrial environment.
Another great question. And so you have to actually turn that around a little bit and think about what the analog is for. There's various different reasons for choosing an analog. Is it purely scientific? And so in that case, if you're looking at, for example, understanding what's going on present-day surface of Mars, maybe it's understanding gully formation, you want to go to some of the driest, coldest places on Earth. So, the Antarctic dry valleys or the high Arctic would be great analogs. If you're purely interested in, understanding cratering on the moon, then, any crater on Earth would make a good analog. The other aspect of analogs we talked about earlier is in using them to test and develop technologies, and also for actually the mission operations. training and developing the mission operations architecture. And there it really does help to have very valid scientific analogs in, as close as you can get desert environments. There's something about, if you were driving through a forest trying to simulate a mission to the moon, I don't think your mindset will be there. So, that's also what makes Horton so unique. You've got this meteorite impact crater, 23 kilometers across. It's big, and it's in a polar desert environment where you're lucky if you see any life form other than you in a day up there.
Cool. So I guess that brings us to the next question by Marianne Denton on Facebook, who asks, what's been the most memorable field experience or discovery that you've experienced?
Experience and discovery is, perhaps two separate answers, but probably both have occurred up on Devon Island in the Canadian Arctic. One was still most exciting discovery for me, which really started me on this whole, astrobiological track, was, as often happens, on the second to last day of my first field season at the Horton crater, was when I discovered the, really concrete, conclusive evidence for a hydrothermal system in that crater. And it was this beautiful, big, about the size of my office, this big kind of geode, essentially, just kind of sparkling. And I was like, wow, this is just fantastic. And it was in the breccias generated by the impact. So it had to have come after the impact. And so, that was one of the most amazing discoveries. And then, experiences, still, I still keep getting asked questions about this. I was on Devon Island last summer on the south coast, and woke up, first morning at camp, woke up at 6 a.m. and there was a polar bear trashing a tent and 3 other white fuzzy things on the sea ice right by camp. And so that was, quite an experience for other reasons, but kind of bringing to home that we're working in a pretty remote part of the world that was literally on the shore of the Northwest Passage. And I've had many experiences in the field and, dealing with adverse weather conditions and other things, but that was my first very up close contact with polar bears, which roam the north.
Wow. This makes me think of another question. You mentioned that you've been working in the high Arctic for 20 years or so. Have you been seeing some of the environmental change caused by global warming up there?
Yeah, absolutely. And you wouldn't think on a 20-year time scale you would. But this coming summer, I actually came to Canada 20 years ago this June. And so, this summer will be kind of 20 years from my first field season to another field season. And more extreme weather. It rains a lot more in these polar desert environments than it used to. I do see, pretty drastic changes in the sea ice. You fly. I'm not really working around sea ice, but on the flights, up to the Arctic and things, I typically go up at a very similar time each year. And, there's fluctuations, but year on year, it's progressively kind of, less sea ice when I get up there. And, it's breaking up earlier and forming a lot later and less aerial extent. I've started doing quite a bit of work on not crater related now, and which has taken me up to the Arctic this summer. On comparative Mars planetology, looking at glacial and periglacial geomorphology, so looking at kind of ground ice too. And so starting to look, I actually had an undergrad student do a project on mapping changes and recession of glaciers up in the Canadian Arctic, and the numbers are pretty staggering as to how many of these glaciers have receded or even disappeared in the time we had the first air photographs in the 50s to the present day.
Sometimes you wish you could grab a politician by the scruff of the neck and bring them up there. But a topic for another time. On a lighter note, though, you probably remember about 15 years ago, maybe more now, there were these movies, Deep Impact and Armageddon. Armageddon. What did you think of those?
It's funny, I still use those in talks that I give. But if I remember rightly, it's early 90s, maybe even 1992 or something. So, we're maybe showing our age a bit here, Sanjoy, because I'm sure a lot of listeners were not born in the early 90s. I was in high school, I guess. I do remember them coming out, and it brought, I think, to the into the Hollywood and to public the idea that things can and do hit the Earth. Maybe offline I'll tell you about what I actually think of those movies.
I was hoping the camera would hide the gray hairs that are slowly appearing here, but can't escape age. But I'm going to own it. So the PhD process is never a linear path, and it can be difficult and ups and downs emotionally to get this degree. Perhaps you can talk about your experiences and if you had any mentors that helped you along the way. Just a lot of people who are starting graduate school can get intimidated by the PhD obtaining process. But I just want to emphasize that it's not a lonely process, and perhaps you can share your experience as well in what you went through to get the degree.
Well, lots one could talk about. I was just kind of thinking before the show too. I actually never applied to university during high school because it wasn't, on my radar. It wasn't what I thought I'd be doing as a teenager. And I think that's something I try and tell my grad students and my current PhD students who are, worrying a lot about the future. And, what's always worrying about what's next, what's after PhD. I think there's a lot of just kind of enjoying the moment, enjoying what you're doing, and not worry too much about the future. So as an undergraduate, I had no idea I'd be doing a PhD. If you asked me back as an undergrad or even a PhD student, if I'd be on this show and a professor at Western, I probably would have laughed at you. I tried a lot of, getting a lot of different experiences during PhD, getting some teaching experience I found very rewarding, and I enjoyed that as a PhD student, helping undergrads kind of learn geology, and I found that rewarding, and, that's what made me start to think about, potentially becoming a prof in academia. I took time out, kind of after PhD with them in government, working at the Canadian Space Agency before coming back to academia. Increasingly now, you said lonely exists. So I was actually at a university where there was a few of us working on impact craters, but I was really the only one doing kind of planetary science related research. So, I did struggle with that at times, and that's why conferences were so important to me. And I made a point of, either convincing my supervisor to get me to a conference, or, making your own way, and, applying for all the scholarships and things that I could to get me travel funding to attend conferences like the Lunar and Planetary Science Conference that, I attended that in the first, 6 months into my PhD down in Houston. And, that was fantastic because here I am now surrounded by, thousands of people, like-minded people. And, back then there was email, but, now I'm on social media and on Twitter, and, I do think it's easier to keep in touch and reach out. Just this morning, I actually had a Skype chat with, this was someone, a PhD student at some university. I'm not going to name them or the university. We just sent out on Twitter, I'm interested in doing field work, some field analog studies. Someone tagged me on that post, and I said, yeah, sure, happy to chat. And, and we had a Skype chat this morning. And so, yeah, don't be shy of reaching out, and especially on things like Twitter now. I think it's a lot easier to do.
Yeah, those some beautiful words to end with, Gordon. Again, those of you who are watching interested in the graduate work in science, don't feel shy to send out an email to people, knock on doors. And the experience of graduate school is one where the community matters to your own mental health and to your own success in graduate school. So, Gordon, it's been an absolute pleasure chatting with you today. Thank you so much for taking the time to chat. I know you're extremely busy, particularly as chair of CPSX. So perhaps if you have some final words of wisdom, but if that, thank you. What can I say? Thank you. This is amazing.
You're totally welcome, Sanjoy. And I can't believe an hour has passed already. It's been fun, and I could definitely talk about these things and keep on answering questions for many more hours. And I think we're in exciting times. We're going back to the moon and getting a bit closer to having samples coming back from Mars and then getting humans to Mars. And so, the young students out there listening, this is I think your generation, an exciting time to be in science. And I'll do a plug for impacts again as a really important process to understand and to learn about. And to be honest, it's a field where we do need more people studying impacts, not just on the Earth, but other planets too. still room for discovery, which I really find exciting, and that hopefully you will too.
Thank you again. And you tweet us at Dr. Crater on Twitter. Those of you who are watching live and who will probably hopefully see the recording as well, what do you all think about impact craters? How do you think that has impacted the, well, pun intended, the origin and evolution of life on Earth? And please join us next month for Ask an Astrobiologist. And until then, please stay curious. Bye now.